The Cafferty Group, technical service advisors with offices located in Nebraska, Iowa, Kansas, and Colorado, presents Essential HVAC Principles, Gas Heating Fundamentals. Combustion Theory. Oxygen, heat, and fuel are the trihedral that make combustion possible. Oxygen, required to fuel the burning process. Fuel, materials such as coal, gas, or oil that is burned to produce heat or power. Heat, ignition is provided by a flame, spark, or a hot enough surface. Incomplete combustion occurs when there is improper air and fuel mixture, insufficient air supply to the flame, insufficient reactant residence time in the flame, low flame temperature, flame impingement on a cold surface. Ignition temperature. The fuel-air mixture will not burn freely and continuously below the ignition temperature. Chemical reaction between the fuel and air may occur. Here are a few flammability limits and ignition temperatures of common fuels in fuel-air mixtures. Carbon, molecular formula C. There is no lower or upper flammability limit in percentage. Ignition temperature, 1,220 degrees Fahrenheit. Carbon monoxide, molecular formula CO. Lower flammability limit, 12.5%. Upper flammability limit, 74%. Ignition temperature, 1,128.2 degrees Fahrenheit. Hydrogen, molecular formula H2. Lower flammability limit, 4%. Upper flammability limit, 75%. Ignition temperature, 968 degrees Fahrenheit. Propane, molecular formula C3H8. Lower flammability limit, 2.1%. Upper flammability limit, 10.1%. Ignition temperature, 870.8 degrees Fahrenheit. CO2 versus O2 natural gas mixture. Flame color with low air is yellow. Flame color with the proper air is blue. Flame action with low air is soft. Flame action with high air is hard. Magic numbers. 4% oxygen at 9% carbon dioxide equals 21% excess air using natural gas. Proper combustion must be maintained to operate safely and efficiently. Oxygen and carbon dioxide. Use them to adjust the burners. Consider BTU content and air density. By obtaining appropriate combustion, you'll meet the burner rated capacity. It limits carbon monoxide production, provides a steady flame, and minimizes nuisance shutdowns. Carbon monoxide exposure. As for the concentration of carbon monoxide in air, 9 parts per million is the maximum allowable concentration for short-term exposure in a living area, according to ASHRAE. 35 parts per million is the maximum allowable concentration for continuous exposure in any 8-hour period, according to federal law. 200 parts per million will give you a slight headache, tiredness, dizziness, nausea after 2 to 3 hours. This is the maximum CO concentration for exposure at any time prescribed by OSHA. 400 parts per million. Frontal headaches within 1 to 2 hours. Life-threatening after 3 hours. Also, maximum parts per million in flue gas, according to the EPA and AGA. 800 parts per million, dizziness, nausea, and convulsions within 45 minutes, unconsciousness within 2 hours, death within 2 to 3 hours. 1,600 parts per million, headache, dizziness, nausea within 20 minutes, death within 1 hour. 3,200 parts per million, headache, dizziness, and nausea within 5 to 10 minutes, death within 30 minutes. 6,400 parts per million, headache, dizziness, and nausea within 1 to 2 minutes, death within 10 to 15 minutes. 12,800 parts per million, death within 1 to 3 minutes. Proper flame color. Clear inner cone or dark blue inner cone. Light blue outer mantle. Proper air mixing. Primary air, pre-mixed. Secondary air, air over flame. A 10-to-1 mixing ratio. Improper flame color. If it's because of lack of air, the flame will be yellow or orange and soft. It will be sooty, with high carbon monoxide production. Excess or too much primary air. Flame would be very blue and noisy. No soot, but a small flame. Excess gas, you'd have too large of a flame. It would be yellow, with high discharge stack temperatures and high carbon monoxide production. Excess gas pressure is not good. Can cause a blowing sound. Carbon monoxide production. The flame extinguishes. Raw gas in the heat exchanger. High flame velocity. Bad LP gas supply. And lifting flames. Gas characteristics. All gases have different specific pressures. All gases have different heating values. Gas values are not constant. They are area dependent, and they are close in value. Here are some characteristics of fuel gases used straight or mixed for domestic service. Natural gas, specific gravity 0.57 to 0.70, BTUs per cubic foot gross 900 to 1200, and the ultimate percentage of carbon dioxide 11.7 to 12.2. Refinery gas, such as fuel oil, specific gravity 0.88 to 1.0, BTUs per cubic foot 1,470 to 1,660. The ultimate percent of CO2 13.6 to 14.4. Butane gas 1.95 to 2.04 specific gravity. BTUs per cubic foot 3,180 to 3,260. The ultimate percent of carbon dioxide 14.0. Propane gas, or LP. Specific gravity 1.52 to 1.57. 2,500 to 2,580 BTUs per cubic foot. And the ultimate percent of carbon dioxide 13.7. Natural gas. Nearly odorless. For safety purposes, odorants are added to natural gas and to LP gas to give them noticeable odors. It is colorless. The composition of natural gas depends on its geographical source. Gas is drawn from various sources, and the composition that is distributed can vary slightly. Local gas utilities are the best source for BTU values for a particular area. Heating values of natural gas vary from 912 to 1,208 BTUs per cubic foot. The usual range is 1,001.10 to 1,049.41 BTUs per cubic foot at sea level. Heating values of substances occurring in common fuels. Below, see the list of higher heating values and lower heating values in BTUs per pound and density per cubic foot for carbon to CO, carbon to CO2, carbon monoxide, propane or LP, and butane. LP, or liquefied petroleum gases, consists primarily of propane and butane, usually obtained as a byproduct of oil refinery operations or by stripping natural gas. It can be liquefied under moderate pressures at normal temperatures. It is a gas under usual atmospheric conditions. Forced air systems. The blower is responsible for moving the air throughout the home. The heating elements, or heat exchanger, is responsible for heating that air that is forced across the heat exchanger. When air passes across a hot surface, the air temperature rises. When a motor and blower wheel are added to the heating box, you have forced air heating. It moves air through a home faster and more efficiently than the natural convection equipment, and it utilizes a smaller heating box and ductwork. The heat exchanger. When gas burns, toxic fumes, including carbon monoxide, are emitted. To keep those toxic gases separate from the air, the heat exchanger is used. A heat exchanger is simply S-shaped metal tubes. Gas burns inside the tubes, and the toxic gases are vented out of the home using a flue pipe. The blower motor forces air past the outside of the tubes, heating the air as it does. This keeps the toxic flames separate from the clean air that is blown into the home. The pressure switch. A pressure switch is used to make sure that the inducer draft motor is on and pushing gases out of the vent pipe. If there is a vacuum created by the inducer motor, the diaphragm will pull in, activating a switch that continues the sequence of operation. If it does not sense a vacuum, then the switch will remain open and the sequence of operation will start over. Igniter and pilot lights. Gas furnaces need a way to light the gas to start a flame. Earlier designs used a pilot light, which burned constantly, igniting the gas as it entered the combustion chamber. Modern furnaces use a hot surface igniter, or HSI, that will glow red hot, or a direct spark igniter, which ignites the gas. Burners. A burner is where the gas and air are combined, creating a flame that becomes the heat source. Thermocouple. A thermocouple is used with a pilot light to sense whether or not the pilot light is lit. It uses two small metal wires inside of a tube that, when heated, conducts electricity and sends a DC voltage signal to keep the gas valve open. If the thermocouple is bad or does not sense heat, then it will shut off the gas valve. Gas valve. At the point where natural gas comes into the home, the pressure is usually between 8 and 12 inches of water column. It enters the gas valve and is stepped down to the correct pressure for the furnace, usually 3 to 5 inches of water column. With some gas valve designs, the gas is drawn out of the valve by the combustion blower and is therefore at a negative pressure as it enters the burner. The gas valve controls the gas going to the furnace, including shutting off the gas when a safety device fails. Flame sensor. A flame sensor works as a safety to detect heat when a hot surface igniter is used. If it does not detect heat, it will shut off the gas. Flame rectification. Flame sensing rods, also known as flame rectifier rods or flame rectification rods, are commonplace in modern hot surface and ISI or intermittent spark ignition gas-fired appliances. During the ignition sequence, the gas furnace undergoes a process where either a spark or a hot surface igniter will ignite the gas. As the gas is ignited, the flame sensor creates a current of electricity. The electricity is quantified into microamps. If the gas furnace's board does not read the proper level of microamps, the furnace will quit giving the system fuel to prevent an explosion. Draft inducer motor. Since gas, when burned, gives off toxic fumes, it is necessary to vent the fumes from a home through a vent. A draft inducer motor turns on before the gas is allowed to burn and stays running as long as your system is heating. This creates a small vacuum and pushes the air out of the vent pipe. Blower motor. A blower is used to generate airflow into a home using supply and return air vents. The blower circulates air throughout a home by pulling in air through a return air filter, blowing that air across the heat exchanger, and supplying it to the vents. Furnace limit switch. If a furnace becomes too hot, a limit switch is used as a safety to turn off the gas. For example, if a blower motor stops working and no air is being circulated, temperatures will rise inside the furnace. If this happens, a limit switch will shut off the power to the gas valve until the problem is fixed. Gas furnace sequence of operation. 1. Heat call from the thermostat. 2. Control board does a safety check, limit switches, rollout switches. 3. Inducer motor comes on. 4. Pressure switch must close to go to the next step. 5. Hot surface igniter begins getting hot, or direct spark igniter begins to spark. 6. Gas valve opens. 7. Furnace lights. 8. Flame sensor senses flame. 9. 30 seconds to 1 minute later, the blower will come on. 10. Once the thermostat is satisfied, the burner shuts off. The blower continues to run for a predetermined amount of time. Thank you for joining us for Essential HVAC Principles, Gas Heating Fundamentals. If you have any questions or need more information, please contact the Cafferty Group Technical Service Advisors at one of these 12 locations.